Okay, once more with feeling. So we've got this last one. This last one does have an oblique asymptote because the top is 1 degree higher than the bottom, and it's not like that first one where we would have had to do a bunch of expanding to find it. So this one I will actually show you how to find the oblique, review that from advanced functions. Yeah, I don't think I'll ever put an oblique on a test or anything like this. So this one, just so you have seen it before in a calculus sense, but I don't think I'll ever test you on this. So we begin. X-intercepts. There's none because that numerator is never going to equal 0 because you have 3x squared plus 4, so x squared is never going to be negative, so when you add 4 you're never going to get back to 0. So that's going to be that. The y-intercept, when I plug in 0 I get 4 over negative 2, so that's going to work out to negative 2, so there's our y-intercept. Vertical asymptote, at x equals 2. Horizontal asymptote, none. And we are going to get this oblique asymptote. So if you remember, to find the oblique asymptote, you have to kind of divide the top by the bottom. So I'm sure, coming from Marshallin's class, you are a synthetic divider. So you can go ahead and divide that using synthetic division. I never learned synthetic division, and I refuse to learn synthetic division. I like my long division, so I'm going to go with that. So there we go. So we're doing that. Remember, you do have to put the placeholder 0 for the 0x in the middle. Pretty sure you have to do that with synthetic division as well. So how many times does this go into 3x squared? Well, it goes in 3x times. 3x times x minus 2 is that. We're going to subtract that off to see what's going on. I'm going to get positive 6x. Drop the 4 down. How many times does x minus 2 go into plus 6x plus 4? Well, it's going to go in plus 6 times. 6 times that is going to be 6x minus 12, something like that. Subtracting that off, and I get 16 as my remainder. And what that turns into so this was our original thing. We did the division, and we ended up with 3x plus 6, and then my remainder was 16, so there's 16 that hasn't been divided by x minus 2 yet. And basically what this works out to, why this turns into the oblique asymptote. So this part's my oblique asymptote. And why that's the case is because when x gets really big, this last term that hasn't been divided yet, when x is a million, pretty much turns into 0 as x gets really, really big or really, really negative, because you're doing 16 divided by a huge number. So overall, the function's going to look just like that line when we're really, really, really big. So there's your oblique asymptote. First derivative. So I'm going to run through quotient rule without writing out the different parts first. That's risky because I've screwed up the first two and had to edit the videos, but I'm going to power through. I believe in myself. F primed times g. Oh, I've got my function right there. I don't have to write it out. Minus g prime, which is 1, times f all over g squared. Like so. There we go. Nothing to common factor on top, so we're just going to, but we can expand that right away. Something like that. And something like that. Looks like that numerator does not factor. So to get my critical values, I'm going to need the quadratic formula. Well, there's your quadratic formula. 12 plus or minus the square root of 192 all over 6. So I don't have to get super accurate because we're a lot of decimal places because we're just going to sketch at the end of the day. So those are my two x values there, and we also have the x equals 2 from the bottom as a kind of critical value. All of those things are going to go in my factor table. Negative infinity, negative 0.3, 2, and 4.3. And we have just the quadratic, 3x squared minus 12x minus 4, and we've got the x minus 2 squared. So with the squared there, that thing's always never going to be negative, I should say. And then the quadratic, again, did this in a different video, but it's a quadratic that opens up. So it's going to be negative between its x-intercepts. So its x-intercepts are the decimal numbers, and it's going to be positive outside of there. So we are positive, negative, negative, positive. 2 is our vertical asymptote. Both of these, so these values from the quadratic formula make the numerator 0. So they're both horizontal tangents because the derivative is 0 there. The first one is a max, the next one is a min. I'm going to plug into the original function and get y values for both of those x values. This looks like fun. Now this one I got like negative 1.9 if I round it off to one decimal place. 4.3. I got 25.9 for that one. All right. So from there, now we need the second derivative, if I can find my first derivative. So there it is, 3x squared minus 12x minus 4. Bear with me. Yep. So there's my parts. F prime g minus g primed f. All over g squared. I can factor out one of the x minus 2's. Those cancel. And then I think it's just going to be expanding that big square bracket. So we're going to get 6x squared minus 12x and minus 12x. So minus 24x and then plus 24. And then a minus 6x squared plus 24x and a plus 8. All over now, x minus 2 cubed. Oh, look at this. Aren't I good at making questions? We just got 32. So that's nice. So, just looking at that second derivative, I'm not going to do the full factor table. It's never going to be negative because the top's 32 and the bottom is x minus 2. Oh no, it's cubed. Ooh. Run away. Sorry. Looking at that second derivative, I know that it's going to be negative when x is before 2 and positive afterwards because it's just based off of that bottom term there. That looks better. That's our vertical asymptote anyway, I believe. So that is not going to affect. So we have minus infinity, minus 0.3 to 4.3. Am I remembering that right? Yep. Those are my values that are going to go in my combined table. First derivative was negative between the two decimal things and positive outside. Second derivative was negative before 2 and positive after 2. So we're going to be increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. And I believe this was my min, and this was my max, and that's my vertical asymptote. And I've got those x values up above. Oh, I have those. Yep. Oh, I'm good. Max and min, yeah. Minus 1.9, 25.9. So let's see if we can sketch this thing. So we need a minus 0.3, a 2, and a 4.3, something like that, we'll call it. This is going to be a negative 1.9. Dot there. Horizontal tangent. Way up here at 25.9. Another dot. What else do we have? We had no x-intercept, I believe. And my y-intercept is negative 2. Something like that. And then we've got this oblique asymptote, so it's at 6. So say a quarter of the way up to that other point. It was 3x plus 6. Wasn't it? Yeah, 3x plus 6. And so it's got a slope of 3. If I'm just doing a rough sketch, I just really want to see, does the line go above or below that point? So 3x plus 6 when x is 4.3, so 3 times 4.3 plus 6. That's 18, so the line's going to go below that, 19 if I round. And then at negative 0.3, 3 times negative 0.3 is that, plus 6 is that, 5.1, yeah, so it's way up here, something like that. So my oblique, something like that. So I just plugged in some values into y equals 3x plus 6 to see if the line's going to pass below or above those points. So something like that. And let's see if we can draw this thing. So we have the increasing concave down with a max there. So it's going to start near that asymptote, flatten out there, and then switch to the other shape and head to the vertical asymptote. So something like that, I believe. And then pick up the vertical asymptote with this shape. So we're going to have to start up here. Hit this horizontal tangent minimum, and then continue with this shape, but get close to that asymptote. So I don't know, something like that. And that's my picture. I'm zoomed out all the way, so I can't look at the full picture all at once, but there we have it. So that's something you could do with an oblique asymptote if you ever ran into one of those. Something like that would work. Okay, so there's some practice that you can work on when you're in class.